Recording is rolling. Welcome to Monday, October 4th. Uh, we started centripetal force, centripetal motion. Now, in AP terms, this is Unit 3, and AP kind of designs the unit this way. We're actually going to take two different ideas and combine them. So, centripetal force, this was the lab you guys did last couple of days from last week. Also, remember I had you guys do a lab write-up, but we never got to it. So one of the things we're going to do today is I'll take you guys over an AP style lab write-up. You guys can grade yourselves out of 12 points. And by the end of today, I do want to introduce to you guys universal gravitation, maybe like the tail end of today. And we're going to eventually tomorrow like bring these together and talk about orbits. Okay? So that's the plan. You guys have a page clipped to the front of your desk that looks like this. These are chapter 7 questions from your book. Now your book doesn't line exactly 100% with AP, but this is the closest chapter, so this is what we're going to be doing, chapter 7. And I think that what we did last time worked out really well, where I gave you guys a main homework that involved problems that we pretty much covered in class. And then I gave you guys a bonus homework opportunity, which is if you want to have extra practice, then there you go. If you turn those in, you get even more points. All right, so let's do the same thing. So here's those. Also, this assignment's listed on Focus. The prompts are listed out, and also on Google Classroom. I typed these up, and so these are in multiple places. Picture retakes are tomorrow, if you wanted that. And let's take a look at the starter question. Oh, no, one more thing. Top scientists. Yeah. So over the weekend, grade you guys' dynamics quizzes, and oh, look at you guys. Look at all those top scientists that got there. So if you see your name out there, you did really, really awesome. Now, I do want to, of course, get you guys quizzes back as soon as I can. I'm still waiting on a couple of late entries. Then I will post once I have all the quizzes in, I'll post the solutions. I'll get you guys your quizzes back. And I think what else has also been a good idea has been working for us is give you guys an opportunity to turn in corrections for half credit back. So they'll all in time. But if your name's up there, then awesome job. All right, so now start a question. What is the tangential speed of the puck on the air hockey table? So here's a puck on air hockey table. That means no friction. So there's no friction. In order to maintain dynamic equilibrium. Now, when I say dynamic equilibrium, remember what that means. So that would be maybe in contrast to static equilibrium. So this bottom weight down here, this M2, that might be in true static equilibrium, where maybe if there's a weight down and a tension up and everything's just balanced out, it's not moving. But what about this top puck that's moving in a circle? Is anything moving in a circle in true static equilibrium? No, because it's going around a curve. And Newton's first law of motion says that either objects are at rest or if they're in motion, they want to keep moving in a straight line. And either of those cases will be true as long as there's no net force. If something's going around a curve, there must be a net force on it. A centripetal force, which is the tension in the string, which is also equivalent to and provided by this hanging weight. Okay, so I wonder what the speed, like the radar gun speed, the tangential speed of this puck would have to be so that this radial size does not increase or decrease. It stays constant. That's what you guys were doing back on Thursday and Friday. You guys figured this out experimentally, different groups, put you guys all together. Did anybody figure out the answer? Oh, yeah, got it? Oh, no? We got it. All right, well, I will take you guys through this. It's good warm up. So, do this way. Got here. I know that the answer to the lab that you guys figured out empirically is that centripetal force is equal to mv squared over r. You guys know that. We're solving for this v. Now, remember that centripetal force is never a force unto itself. It's never a force in isolation. It's always caused by one of the classic forces that you're already familiar with. It might be a tension, it might be a weight. Some examples there. It might be a normal force, it might be a friction force, but there's one of the classic forces is always acting as a centripetal force to hold something in a circle, if something like that's going on. So in this case, wouldn't it just be the weight of this guy, this M2? Is 3 kilograms the centripetal force? Is it 3 kilograms? Are forces ever measured in kilograms? No. Forces are measured in what? Newtons. So how many newtons of weight is this? About 30 newtons, because this right here is actually m2g, isn't it? That's what's equal to, well, I'm just calling this top one just plain m. Okay, so these m's are different, right? Got m and m2. Let's solve this in terms of variables, because that's a good practice to do for AP. Well, maybe we'll throw a subscript. We'll do a subscript one. Let's do that. M1 and M2. Okay. Multiply to be R. That'd be M2 GR. Divide out the M1. That's all equal to V squared. Okay. And then finally, take the square root of both sides. The speed would have to be the square root of M2 GR all over M1. Okay. Yeah. Now that's the general solution. I wonder what it is if we plug in the made up numbers that I did. We got, let's see, square root. M2 was 3 kilograms. This is in a gravity field of about 10 meters per second squared. The radial size of the circle is 0.75 meters, or that's about 75 centimeters, about 3/4 of a meter thick. And then all divided by M1, which I listed as 0.25 kilograms, which is, well, half the size of this. So basically one of your medium-sized lab weights. Actually, the numbers on my native example aren't too different from your lab numbers. So let's see how this plays out. So I've got a giant square root, 3 by 10 by 0.75 on 0.25. Yep. I'm getting about 9.5 meters per second. That's what's going to maintain the size of the circle and also take that hanging weight and put it in true static equilibrium where it's not moving up or down. There you go. About 9.5 meters per second. And you know what? This value right here is actually pretty close to your lab numbers too. You guys were getting speeds of somewhere about there, about 5 or 10 meters per second. How's that possible? Well, because your circles had a very similar size to my native example. And also the ratios of the masses of your two Play-Doh canisters were probably pretty similar. Ballpark idea of what I have here. Light one on top and heavy one on bottom. Like that. You feel about like that. Okay. Guys good so far? Now there's a few places I want to go with this. I'm going to do a bunch of examples with you guys, all related to centripetal force. We won't get to universal gravitation until the tail end in the class. But something else I'm wondering about this is, if you look on AP's equation bank, they don't actually list this formula, centripetal force is mv squared over r, but they list one that's very similar to it. Do you guys see centripetal acceleration is v squared over r? I'll show the camera right there, show you guys. Okay. V squared over r. That sure does look a lot like this, doesn't it? This mv squared over r. Because all you have to do is combine it with Newton's second law of motion to get that. So if I know centripetal force is mv squared over r, and then Newton's second law of motion says acceleration is force divided by mass. Divide both sides by mass, get acceleration. That's Newton's second law of motion. Centripetal acceleration, therefore, is equal to just plain v squared on r. Okay? And that's what, that's the AP formula, AP version. So similar idea. And why am I bringing that up now? Because I'm curious to know what the centripetal acceleration is of, say, being on that hockey puck. What's that value? Right? Could you imagine if you were a fly just flying around, and you see that, like, hey, I'm going to land right there, land right there, and then start spinning around, vroom, vroom, vroom. Do you think it would feel like there's an extra force in addition to your own weight, maybe holding you in a circle? Probably an extra force. I wonder what that would feel like. Like how many G's? You guys ever heard of like G-force? I'm gonna show you guys a demo. I flip my screen over.
G-force is my favorite movie.
Wouldn't know the reference, so sorry.
They're like guinea pigs or something.
Yeah, they're getting
Huh. This sounds interesting. Maybe one day. Right, so let's look inside this centrifuge. Well, we'll start on the outside. So got NASA astronauts in training, fighter pilots will be in this type centrifuge, sitting in one of those boxes. Suppose your back is to the outside wall and you're facing towards the inside of the circle. do you think you would feel like you're being thrown outward? You would feel that way. Is there any actual outward force throwing anybody outside? No. There's the back wall holding you in a circle. You think the faster you go, the more that force would ramp up? Sure would. Okay. Now, here's the difference of perspectives here. If you're inside one of those boxes, you think you're being thrown outward. That's because you're in a rotating frame of reference. You think there's a centrifugal force. But from our point of view, from the camera's point of view, from our inertial frame of reference, there's no such thing as a centrifugal force. There's only a centripetal force. Okay. Now that you guys know that, let's go inside this thing.
It's ready. Final ready. Case.
You guys see a G counter in the top left? It says basically 1 Earth G. It's just its own weight. Okay, so 1 Earth G. We're all in 1 Earth G right now, right?
Squeeze handbrake. Handbrake is activated. Work hard. 3, 2, 1, engage. Legs like deep breath. You're on top. Breathe. 1, 2, breathe. Drop the shoulders. Breathe. 1, 2, breathe. Squeeze your legs. Squeeze your butt. Hey, squeeze. Keep squeezing. Keep squeezing. Keep squeezing. Are you there? How you doing? How you doing?
No.
You know what happened?
No, I don't.
Huh?
No.
Yeah, you doing all right? Yeah, he doesn't know what happened. Yeah, so he blacked out. Yeah, blacked out. Because you guys saw he got up to about 9 Gs. So he would feel 9 times as heavy. His heart's trying to pump blood through his vessels, so like 9 times as heavy. Right? You can only withstand that for a few seconds, and that's kind of like the upper limit. Maybe more if it's like a tiny fraction of a second or something. But you got to wear the special suit, do special training, and then if you're, say, an astronaut that's blasting straight upward, that would be a huge acceleration. Or if you're a fighter pilot, maybe like moving really fast and go through a curve. Ooh, through a curve. That sounds like we're bringing it back to this, doesn't it? Either of those cases, that's why you'd have to go through that type training. But I wonder, that fly that just landed on, let's say, this Play-Doh canister from back on Thursday, maybe you put a little fly in there and say, hey, I'm going along for a ride. Ooh. I wonder if that fly felt like that guy. And since all these numbers are pretty similar to your lab numbers, like this speed included, and this radial size, let's figure out what's the acceleration for that fly in your Play-Doh canister back on Thursday. Let's figure it out. Well, we've been going, we just solved for a speed of about 9.5 meters per second. So let's use that number, 9.49 meters per second. According to this expression, we're supposed to square that and divide by the radius of curvature, which I gave to you as 0.75 meters. Pretty close to your lab numbers. See, what was that fly feeling? And remember, I'm not also including the downward effect of the weight, which you just have to do a little Pythagorean theorem. Okay, so I'm going 9.49, square that, divide by 0.75. That's it. Oh boy, 120 meters per second squared. Okay, now that's our classic metric units. How would you convert that to Gs? Because the value you just saw was like Gs.
Divide by 10, right?
Divide by 10 meters per second squared. Let's do a little dimensional analysis, right? Say they're about 10 meters per second squared for every 1 Earth G. Can that be true? Right? Because measuring Gs is really measuring an acceleration. It's like you're quantifying how many units. Maybe I should put 9.8 down here, but you guys get the idea. 12 Gs. 12 Gs. What's that fly feeling?
That fly's dead.
That flies.
Yeah. That's one.
I don't
Fly.
think that fly's feeling anything anymore.
Yeah. He will feel a strong force, and then he will feel nothing.
Poor fly.
What's that fly? Yeah, so. Let's look at a car going around a curve. A car going around a curve. Oh, hold on a minute. No. I almost forgot something. I gotta do yeah. Okay. We gotta do the cup. Let's do a live demo. You guys see this cup? Oh, it's an empty cup. I remember last time I broke out a cup. That was pretty fun. I wonder what this one's gonna be. Oh, we got the water going again. Oh yeah. Got a cup full of water. Yeah. Yeah, that's the reason. Thirsty Griffin. Oh. All right. I wonder if there's a way I could turn this cup upside down and not turn this place into a water park. What do you guys think? Spin it? Think I should spin this thing?
I'm
Huh.
scared.
Ooh, I should go this way actually. Yeah, this looks more fun. Oh, this is a tight spot. Oh man. Well, YOLO. Oh, look at that. Hey, do you think maybe there's a minimum speed that's what barely gets around? Oh, all right. Don't stop there. Very carefully. Huh. I wonder if we know enough physics that we could actually solve for what that minimum speed would be to just barely get it around. Let's try that out. Alright, so I'm thinking that the water was most vulnerable to fall out when it was at the very top. So I'm going to draw this way. Got a cup of water upside down. There's the water. Okay. There was a string. Where's my string ruler? Some straight strings. Okay. It's on this curved path that has some radial value that I'll call R. Okay. Maybe this water has some mass. It might help to anthropomorphize the water, so let's put a little goldfish in here, going along for the ride. Maybe that fish has some mass, and of course there's some speed that we're solving for, because if he's just not in motion, then he's about to fall out of the cup. So there's some speed, and I want to solve for what is that minimum speed. So I'll say V-min, like the minimum speed. Make sure he just gets around. Okay. Now, if you're that fish, let's play around with this a bit, little thought experiment. And just wheel around. If it's wheeling around faster and faster and faster, and let's say you're blindfolded, so you're a blindfolded fish, do you feel like there's a centrifugal force pushing you up towards the bottom of the cup? That's what you think is going on from your rotation frame of reference. Right? You might not even know that you're rotating. Right? You just feel like, oh, the faster I'm going, I feel like I'm being thrown this way. But is there really a centrifugal force? No, there's no force that's pushing the fish upward. No. Right? There's inertia keeping the fish going to the right at the snapshot, and there's possibly the bottom of the cup holding everything in, and maybe that force is increasing on the fish in the water. Right? But there's nothing pushing the force pushing the fish up. Right? In fact, if you cut the string right here, which way would the fish fly? Would it fly upwards or to the right? Fly to the right, wouldn't it? Yeah. It's like a free body diagram on this fish. Do you think that there's a weight pulling the fish straight down? Call it mg. Right? Probably like that, right? And there's probably also a normal force from the cup. But if I'm interested in the minimum speed, just barely get it around, do you think that for the minimum speed case, the fish might be weightless at that one instant? And its own weight is the only force holding it on that curved path? Right? Fish just barely getting around? So when I say centripetal force is mv squared on r, the only force for the minimum case would just be its weight. Only its weight would be mv min squared on r. Is that what that would be? Good so far? Right. Oh, what cancels out? The mass of the fish. Right. So if I put more water in that cup, would it make a difference? No, as long as the radial size doesn't change, something like that, right? Hey, g equals v squared over r. You know what that reminds me of? That right there, doesn't it? Yeah. Solve for v. Well, multiply the r, take the square root. V min is the square root of gr. There's a general expression. Right. Now let's pop in some values. I know Earth is about 10 meters per second squared. And, I know what we should do for R. Let's actually use the radial value of this cup right here. So break out this meter stick. That's about the center-ish of the cup. And this comes out to pretty much exactly 50 centimeters. I'll show you guys. They're like 50 centimeters. Right. So let's call it 50 centimeters. Or 0.5 meters, right? 0.50 meters. It would go from centimeters to meters. rolled 2 decimal places, 100 cents in the dollar. Let's call this 0.50 meters. Okay? I wonder what the speed was of that exact cup for that exact demo you guys just saw. Well, what is the square root of 10 times 0.5? That is 2.24 meters per second. So if you have the cup going, now remember that's a linear speed. Right at the top, if I'd been spinning it at that speed right at the top, then that fish in the water would feel weightless just for 1 instant. If you go any slower, the water's going to fall out. And if you go faster, then you're safe. You might call it like 5 meters per second might be called sufficient speed, something like that. Yes, sir?
So is that just how you calculate the minimum velocity to make it go?
Yeah. So that's the minimum, right? The min. Okay. Later on in this class, once you guys learn a few more things, I'm going to bring in the roller coaster. We'll have a roller coaster going through a loop, and it'd be a very similar question. This will be part of like a larger question. Now let's do a car going around a curve. Okay. I'll have a car going around a flat or a curve. Let's see, on a flat road. When I say flat, I mean horizontal. Like no banks. We'll look at the bank road in a few minutes, but not yet. Okay, so just a flat horizontal road. So we're up here in a helicopter and we're looking down. So there's, I guess that's the sound of helicopter blades. All right, looking down. Okay. We see this curved path in the road, and here's this car going around at some speed. And maybe the question is, what is Vmax? So this car is moving in a straight line with some speed v. Okay. And I wonder how fast that car can go before it would slide off the road. Maybe this road is a dry road, or maybe it's just rain, or maybe it's all iced over. Hey, if this road is iced over, do you think that this car has to go really slow so it doesn't slip off? That makes sense, right? Okay. Got this radius of curvature. Well, here's like what the circle would look like. There's an associated radius of curvature. Call that R. Hey, look how R and V are perpendicular to each other. You guys see that? Perpendicular. And maybe you know the mass of the car. Maybe I need to give you these numbers too. Right. Let's call the mass of the car 1,900 kilograms. Let's call the radial size, say 75 meters. No, let's go 70 because that's 75. 70, we'll call it 70 meters. Like that, radius curvature. And tell you guys what, I've given you one piece of information that you don't need at all to answer that question. And there's another piece of information that is missing that you need to solve it. So what did I give you that's too much information? What do you think? Mass of the car. How many of you guys thought the mass of the car is probably going to cancel out? Yep, you're right. It's eventually going to cancel out. What information did I not give you that you need? Coefficient of friction. Coefficient of friction. Yeah. Okay. So let's do that. Now I'm going to use static friction because we can go up to this point, and as long as it doesn't break that friction, then it'll be all right. Let's call it 0.85. Okay. All right. Now there's enough info to solve this problem. Okay. Well, you guys know centripetal force. You have an expression for it. You guys figure this out in your lab, and V squared on R. Okay, so you know that. Okay. We're solving for this V, and this centripetal force happens to be provided by what force? The friction force, right? Friction between the tires and the road, some kind of horizontal force. So it is the friction force that's acting as the centripetal force. I'm about to do a series of substitutions. Okay? You guys have an expression for friction force. What is friction force equal to? Coefficient of friction times normal force. Yep. So this is actually coefficient of friction times normal force. Now we'll do the static case because I'm like building up to that point. And the normal force is, well, if the road is a flat road, what's the normal force also equal to?
mg.
The weight of the car, mg, isn't it? Now, I'm not going to draw that for you by diagram because, well, you have to think into and out of the paper, like 3 dimensions. So weight into the paper, normal force out. Right? But that is mg. Yeah, weight to the car. Ah, now, you guys see what's going to cancel on both sides?
And
You guys told me this was going to happen. You said, I think that m's going to cancel. Yep, sure does. So if this guy has his car loaded with groceries versus an empty car, does it make any difference? No, because mass cancels out. So after that v, multiply the r, take a square root. So v, and this is really maximum speed. Trying out us. It'd be, see, mu s times g times r, the square root of that. Here's your general expression. Let's plug in some values, like the numbers I gave you here. So that could be 0.85 times 10 meters per second squared times a radial size of 70 meters. What is 0.85 times 10 times 70, the square root of all that? I'm looking at 24.4 meters per second. That's how fast that car can go up to before it would slide off the road. And, oh yeah, Ed?
What do you mean by slide off the road? Like, how, I know this sounds stupid, but like, does a wider road change that number? Why are we not taking in any factors for the wideness of the road?
Okay, so what's holding the car on the road is just the friction force between the tires and the road. Right? That's what's allowing it to curve in the first place. Right? So if the road is really wide or really skinny, then that's not really going to make a difference. Right? Maybe you could argue if like the wheels on the right versus the left side of the car might have a slightly different radial value, so there might be a slight difference there. But that's the only thing you can think something like that. Yeah. So when traffic engineers design a road wider or skinnier, that's kind of a safety thing. Like if the road's really wide, you feel safer. It entices people to drive faster. So yeah, but not really. It does though. So I did. According to Google, this is about 55 miles an hour. Just in case you were wondering how that translates. And suppose that maybe this car goes a little faster than this. What if it goes like 25 meters per second, which is faster than this? Which way would this car slide off? Is it going to slide off? Well, I'll give you guys 2 options. Is it going to slide off this way, or is it going to slide off this way? What do you guys think? Yeah. How many guys say like centrifugal direction? Nobody says that. How many guys say tangent to its motion? Yeah, everybody says that. That's Newton's first law of motion. That's the way it's going to go. Now, if you're a driver inside that car, you feel like you're being thrown to the left, but that's only because you have inertia forward and the left side of the car is pulling you into a circle, right? That's really what's going on. Centripetal. Right?
Why does the car?
Why would it flip? Because the car has some height and its center mass is actually like way up here. Can you guys think of 3 dimensions? Right? So the fact that the center mass is above the tires introduces what's called a torque. We haven't talked about this yet, but you guys ever wonder why the door handle is opposite of the hinges? Like why isn't the door handle like in the middle of the door, like a hobbit door, or closer to the hinges? Because it'd be really hard to open the door, wouldn't it? Right? So there's not only a force, but there's also like a lever arm, right? And so that would, from the car's point of view, like flip the car, right? But yeah, so you have to think about the height of the car. So yeah, we're doing a little simplification. So thanks very much. Right. Let's go 3D with this. So present screen 2. Hey, throw buddy. I'm looking for, where are you? Here it is, cars on wall. That lovely sound plays through the whole video, so what is this? So that is a really steep banked wall. Remember the example we were just looking at was just a flat road, but now we've got a banked road, which could help you go faster on the road, right? You guys ever watch NASCAR? Sometimes you see some really steep banked roads like this. It helps you stay on the road. Right? You guys ever drive? Go around a curve, helps have the bank, right? Now, those motorcycles are in not true static equilibrium, but dynamic equilibrium in the sense that the radial size of the circles they're on are not increasing or decreasing. We're about to get a car going up there. Now the car has much greater mass than those motorcycles, doesn't it? Is that car going to have to go faster, slower, or the same speed as the motorcycles to maintain that radial size? How many guys say the more massive car has to go slower than the motorcycles? Who says faster than the motorcycles? And who says the same speed as the motorcycle? Oh, yep, there's the winners right there, same speed. All right, let's check this out. So when these cars get up here, notice the cars and the motorcycles are all going the same speed to maintain that circle size. Now, if you went a little bit faster, you think you kind of tend to drift up the wall. If you went a little slower, you kind of tend to drift down. What I want to do with you guys here, I flip my screen back over, is show you guys how to set this up to solve it. And maybe one day we will solve it, but at least want to show you guys how to solve it. Okay. So car on a banked wall. I really do like this problem, so go something like this. Let's have a really steep banked wall, just like the video. Really steep banked wall. Maybe it's like a 70-degree angle or something crazy. Sort of big old angle right there. Let's put a car right here. Now our perspective is we're behind this car. We're looking at, here's the taillights. Here's the back windshield. And this car is going around this curve, like into the paper. So you have to think 3 dimensions, right? Car's going into the paper, going around. Okay. Here's the circular track. Okay, you guys see that? Maybe here's the center of the track right here. Okay. So that this car is some radial distance r from that center. Call that r. Okay. All good so far? Okay. Now this car is going to have some weight. Here, do center mass dot center mass. Okay. This car has some weight. Let's pull it straight down. Call it mg. Okay. Now here's where there's actually 2 different ways to solve this that I know of. One is from the driver's perspective. You can actually set this up for dynamic equilibrium with a fictitious centrifugal force. I might show you guys how to do that one day. But the way that AP never wants you to do that though. AP always wants you to solve it in terms of inertial frame of reference. So inertial frame of reference, do you guys think that there's a really huge normal force that's holding the car up? What do you guys think is bigger? The normal force from the road or the weight of the car? What makes more sense?
Wouldn't they be
They'd be equal on a flat road, but remember the normal force from the road is, and you see the direction because I put my ruler there, it's perpendicular to the surface, of course, right? Not only, wait, what are you saying? It is the weight of the car on a flat road, but this normal force not only has to hold up the weight of the car, it additionally has to pull it into a circle, doesn't it?
So it's more.
Has to be more. The normal force might do something kind of like this. Okay. Notice that's a big old normal force. Okay. And if you split that into components, that normal force is partly holding the car up against gravity and partly pulling the car in. Okay. Like that? Is that true? Hey, is this right here equal to mg? Sure would be, wouldn't it? Okay. But you know what else it's equal to is if this angle theta is this angle theta are the same, isn't that mg also equal to normal force times cosine of that angle? Wouldn't it be that? Okay. And then this component right here, which is normal force times sine of that angle, isn't that equivalent to the centripetal force mv squared on r? You guys see that? Okay. So that's the setup for that one. Yeah. Maybe someday I'll come back and solve this with you guys, and if we have even more time, I might even do the dynamic equilibrium point of view with you guys. Right, but I want to move on to, let's start looking at gravitation. Okay, please plant some ideas in the last few minutes of class here, and then right, so for gravitation, universal gravitation. Right. So we've been working with gravity forces for a long time in this class, but I never told you the master formula of where it comes from. Like you guys know, you have a weight, and it has something to do with the mass and the radial size of the Earth. But now you guys are about to get that info. So suppose we got two bodies just floating around in space. Maybe it's a couple of asteroids, maybe it's a planet and a moon, but one has mass capital M and one has mass lowercase m. Some textbooks do m sub 1 and sub 2, some do capital M lowercase m, so see both of those. And there's some distance between the two. Some center to center distance that I'm going to call r. Right? Notice I'm going from center mass to center mass. You guys see that? Center to center. Like that. Right. And these two bodies floating around, maybe like a planet and a moon, are pulling on each other. So here's the planet pulling on its moon, and here's the moon pulling on its planet. Okay. Now, they pull on each other, right? The planet pulls on the moon pulls on the planet. But you guys know which of those forces is actually bigger. They're the same. Yeah, that's Newton's third law of motion. Same force? Really? Yeah, same force, different masses, different effects, and different accelerations. Okay? If these started from rest, they'd eventually just crash into each other. The big planet might move a little bit. The little moon would move a lot more. Or if they are in motion, if they got some tangential motion, okay, then maybe the moon is in orbit around the planet. Maybe the planet wobbles a little bit, but most of the moon accelerates. Right? Centripetal acceleration. Okay? What is this force as a function of all these other things? Well, it goes like this. Force is equal to, so take the two masses, multiply them together. Big mass times little mass. Okay. Divide by the distance between them squared. So divide by r squared. I'll tell you guys why divide by r squared in a few minutes, but finish this off. And then, now if I throw in a proportion, then that would be that's the answer proportionally, right? But to tie this off and make this a full equation, you want to throw in what's called the universal gravity constant g. So here's your formula right here. Multiply the two masses, divide by the distance between them squared, right? Then multiply by this universal gravity constant g. So g is called universal gravity constant. And that's equal to this number right here.
Okay.
Yeah. There you go.
Can you give that to us in like scientific notation?
Yeah, you guys hear Ryan? Maybe we need scientific notation. Because this week and next week, we're probably going to be dealing with a lot of very large and very small numbers. Very large, if we're talking about like the mass of a planet or star, and very small, like this universal gravity constant. So, yeah, let's do that. This is 6.67 times 10 to the minus 11. And then Newton meter squared per kilogram squared. There you go.
This is 5.5.
Yeah, scientific notation. So three significant figures. Nobody knows why this number is this number. It's one of those mysteries of the universe. It's just universal gravity constant is known to be that number. It's measurable, and I'll show you guys that too. Yeah.
Is it actually 667 or is it 2/3?
Yeah, it's been measured as
So
667.
it's not 2/3.
Right. Yeah, it's not a fraction. It's been measured to be like this value. And it almost certainly has more digits that go beyond that, but just nobody knows exactly where they are because it's kind of hard to measure. Okay. Well, let me show you how they actually measure this number. I think I mentioned to you guys too that this right here, this is Newtonian gravity force. This was understood to be true from the time that Newton published Principia up until Einstein. And nowadays we understand it to be an approximation. I think I told you guys last week that gravity is, no, don't take this into the AP exam. On the AP exam, gravity is one of your 4 fundamental forces. But if you take a bunch of graduate classes, then gravity is actually not really a force. It's actually a artifact of the curvature of space-time. Right? But how do you measure this? How do you experimentally verify this 6.67 times 10 to the minus 11 number? Well, here's one way to do it. What if you have, say, a couple of scales, like a balance, right? I've seen something like this, like a balance with some scales on it. Throw a little mass right here. Throw a little mass right here. Call it M. Right? I bet that's all balanced, isn't it? It's all perfectly balanced. It's M and M. It's all balanced, right? Until you do this, until you throw a big old weight underneath one of these guys. I call this mass big M. Okay. You think it's going to tip the scale a little bit, just a little bit, like that, little tiny bit, right? Because there's a little gravity force between these two. How much gravity force? Well, it's proportional to each mass, and it's also inversely proportional to the square of the distance between them. Okay, 1 over r squared, which I haven't told you guys yet why, but we'll in a minute. Right, and what you can do then is you can take another little tiny lab weight of known force, and I'll put a little force down on this. So known force, and that force is equal to, Gm over r squared. So if you know what that force is, let's say the weight of the tiny one, that weight, and you know this m, and you know this m, and you know this radial size, you can back calculate what this g is. And nobody knows why that number is what it is, but it's measurable. That's one way to do it. How about this other question of why proportional to 1 over r squared? Okay? Now, it probably makes sense why radial distance would be inversely proportional to, gravity force would be inversely proportional to radial distance. Because if things are getting further and further from each other, wouldn't you have a weaker gravity force? Like what pulls on you more, the Earth or Mars? Well, Mars is so far away, the gravity pull is negligible. Okay? Maybe a tiny amount. But why squared? Why squared? But here's one way to think of it. There's actually a lot of phenomena in physics that taper off 1 over distance squared. So I'm going to do a candle analogy for inverse square law. Because I think this makes a lot of sense in terms of light, and then you could just extrapolate and say, oh, how's that for the gravity? Okay. So suppose you have a candle. Here's a candle flame. It's emitting light in all directions. But what we're going to do is we're going to rope off one particular cone of light. Let's say light that's headed kind of horizontally. That's what dash lines for. But say we're focused on this particular cone of light. 3-dimensional cone, right? It's going off. Okay. It's not all it's doing, but it's part of what it's doing. Okay. And then I'm interested in, well, what are some distances I could rope off? Let's go, say, origin point. Let's go 5 centimeters away, 10 centimeters away, 15 centimeters away. Just keep going, right? I'm going to call those distances R, 2R, and 3R. R, 2R, and 3R. Okay, so the original distance, double that distance, and triple that distance. Okay, so I'm getting further and further away. I wonder how much light is reaching my eye as I get further and further away. Well, it's got to be less and less light. Like, if you're really close to the flame, it's like, that's intense. If you get far away, it's like, okay, I can see it, but it's getting dimmer. I wonder how much light you would catch in this place. Now, it would really be circular, but just to simplify this a bit, I'm going to make it a square. So what if I rope off a square and think 3 dimensions, so I turn the square to the side. I say I can catch that much light right there. Patch that in. Right? So I'm catching that much light. Is that? Okay, how would that compare to, say, if you backed up to like twice the distance away? Wonder what that looked like. Do you guys see that this new square I'm making is twice as tall? It's twice as tall, isn't it? Hey, twice as tall. Do you think it's gonna catch, like per unit area, like 1/4 of the original light? Or sorry, and half? Oh, that's wrong. The answer is a quarter. Get my merge mixed up. So let's make another square. So we're just blowing this up proportionally. you guys do see that this new square is twice as tall as the other square, right? It's twice as tall. But you know what? It's also twice as far back into the page. You have to think in 3 dimensions. So don't forget that too. Okay? And where's the original square compared to the new big square? You guys see that the original square is only a quarter of the new big square? Ah, so per unit area, you're only catching a fourth of the light that you were originally. Okay? Let's go back up to 3 times the original distance, right? 3 times. Make a big old square right here. So this square is going to be 3 times as tall, but don't forget, it's also 3 times as far back into the page. That's part of the story too. So 3 times as tall. Okay, let's say 3 times as tall, right? But also 3 times far back into the page. So that, any one of these original size squares, see it's like 1/9 of the original, of the whole thing. 1/9. So you're catching 1/9 of the light by being 3 times as far back. Guess that? That's an inverse square relationship. The amount of light you catch is the amount of light that you catch per unit area is proportional to 1 over the distance squared. Okay. Gravity works the same way. Electrostatic force works the same way. And so if you live in a 3D spatial universe, then that's how that works. Okay. So go back to universal gravity formula. And we got, okay, so explain how the constant is experimentally measured, explain why 1 over distance squared. You know what, another good application of this is, let's take this down to just a planet. So we've got a planet. Okay. Where does your weight come from? It's basically that formula. So here's you have some mass little m. The whole planet has mass big M. Okay. Now, the mass of the planet is distributed over, well, there's like grains of sand all over the place. Some of them are further from you, some are closer to you, some are more to your left, some are more to your right. But the net effect is like the left and the right sand grains cancel out. Further and closer, sort of same deal. Right? So the net effect is that you can treat the mass of the entire mass of the planet, which is spread out over the volume of the planet, as if it were centrally located. And the distance between you and the planet Earth is the radius of the planet Earth. Right? See that? So your weight, I'll say force, meaning your weight, the gravity force between you and the Earth, right, is equal to GMM over R squared. But what I usually try to do is use capital R for a fixed radial size, like the fixed size of a planet, and use little r for variable. So I try to stick to that. Hey, how about this? You guys know Newton's second law of motion says acceleration is a force acting on a mass. This is Newton's second law of motion. Can you combine these 2 ideas and get free fall gravity on a planet? And it would just be this divided by the mass of whatever's accelerating, right? You guys know that all, this goes back to the Galileo experiment. Large masses, small masses, they all accelerate at the same rate. Hey, look at that. And the last thing we'll do today is I'm going to plug in the values for Earth. So what's G of Earth? Well, we got 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. The mass of the Earth is 5.98 times 10 to the 24 kilograms. And the radial size of the Earth is, oh, whoops, sorry, that's going there, is 6.38 times 10 to the 6 meters. Don't forget to square that value. I wonder what the gravity field is at the surface of Earth. 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 kilograms, all divided by, open parentheses, 6.38 times 10 to the power 6. That's 6.38 million meters for the radius. Remember the distance between anything at the surface and the planet itself is assumed to be the radius of that planet, because that's how we're measuring this. Square that. Now, when I hit enter, what number is going to flash on my screen? And I bet you guys already know the answer. 9.8 meters per second squared. Moment of truth. 9.799. 9.8 meters per second squared.
Not for-
All right. Also, sometimes AP writes it this way: 9.8 meters per kilogram. If you ever see that, same thing. Okay. There you go. All right. So we're gonna continue this adventure tomorrow. We'll talk about orbits and be on our way from there.
Friday.
You guys have a good Monday.